Tonight, we're going to make a claim that surprises most people the first time they hear it. Humanity will probably never build an engine capable of carrying a living human being to another star within a single lifetime. The physics simply doesn't allow it, not with anything humanity currently knows how to build, and no theoretical shortcut has ever made it off the page of a physics paper and into something an engineer could actually construct. But that doesn't mean the stars are closed to us. It means the ship that finally gets us there won't be built to move faster. It will be built to carry something no engine ever could. Time itself, stretched across generations of people who will live, grow old, and be gone long before the journey ever ends. A ship where the crew that boards it will never see the destination, where only their distant descendants, born and raised somewhere in the empty stretch between two stars, will be the ones who finally arrive. By the end of tonight, you're going to see exactly why every faster alternative scientists have ever proposed falls apart the moment you study it closely, leaving a single option still standing: a ship built to carry time instead of speed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why generation ships matter, you first have to understand just how badly space defeats our intuitions about distance. We're used to thinking in terms of hours and miles. A drive across a country takes days. A flight across an ocean takes half a day. Even a trip to the moon, which felt impossibly far in the 1960s, only takes about 3 days at the speeds we can currently manage. But the moon is close, practically next door. The nearest star system to our own, Alpha Centauri, is a different category of distance entirely. It sits about 25 trillion miles away. Light itself, the fastest thing in the universe, takes over 4 years to cross that gap. Our fastest spacecraft, the ones that have actually left the solar system, travel at roughly 38,000 miles per hour. At that speed, reaching Alpha Centauri would take around 75,000 years, a span of time longer than the entire history of human civilization. And that's just the nearest star. Most of the stars you can see in the night sky are dozens, hundreds, or thousands of light years away, distances so large that even talking about them in miles starts to feel meaningless. This is the wall that every serious plan for interstellar travel eventually runs into. Not a technical problem you can solve with a bigger rocket or a smarter engineer. A fundamental mismatch between the size of the universe and the speed at which matter can move through it. So the question becomes, how do you cross a gap that large with human beings still alive at the other end? There are only a handful of real answers, and most of them fall apart the moment you look closely. The first answer people usually reach for is speed. Just build a faster ship. If 75,000 years is too long, build something that gets you there in 70 years instead, or 7. On paper, this sounds reasonable. In practice, it runs straight into the physics of energy and mass. Every unit of speed you add to a spacecraft costs fuel, and that fuel has mass, and that mass has to be accelerated too, which costs more fuel, which has more mass. This is sometimes called the tyranny of the rocket equation, and it punishes ambition brutally. Chemical rockets, the kind that launch astronauts into orbit, are hopelessly inadequate for interstellar distances. They simply cannot carry enough fuel to reach the speeds required. Engineers have proposed more exotic alternatives. Nuclear pulse propulsion, where small nuclear explosions are detonated behind the ship and the shockwaves push it forward. Fusion rockets, which would harness the same reaction that powers the sun. antimatter engines, which could in theory convert mass directly into thrust with extraordinary efficiency. Laser-driven light sails, where enormous ground-based lasers push a thin, ultra-light sail to a meaningful fraction of the speed of light. Each of these has been studied seriously, and each of them faces enormous obstacles. Nuclear pulse propulsion requires detonating hundreds or thousands of bombs in sequence, with engineering tolerances that have never been demonstrated. Fusion rockets require sustained, controlled fusion reactions, a technology humanity still hasn't mastered even for stationary power plants on Earth. Antimatter is the most efficient fuel physics allows, but producing even a single gram of it would take existing technology longer than the age of the universe. And it costs more than anything else humans have ever manufactured. Light sails are the most promising in some ways, but they only work for extremely lightweight payloads, tiny probes weighing grams, not ships capable of carrying people. Even in the most optimistic projections, none of these technologies get us close to the speed of light. The best realistic estimates suggest maybe 10% of light speed, perhaps a little more, with breakthroughs we haven't achieved yet. At 10% of light speed, Alpha Centauri is about 42 years away. That sounds almost reasonable, until you consider what 10% of light speed actually means as a number. It's roughly 67 million miles per hour. Building an engine capable of reaching and sustaining that speed, then decelerating at the other end, is a challenge on a scale humanity has never attempted. And even if we solve it, 42 years is still a one-way trip for anyone who boards. The astronauts who leave would grow old during the crossing. Some would not survive to see the arrival. Which brings us to the deeper problem. Even our best theoretical propulsion systems don't get us to the stars in a human lifetime with any comfortable margin. They get us there right at the edge of what a single human life can endure, if everything goes perfectly. And nothing in space goes perfectly for 42 straight years. So scientists and engineers have spent decades looking for a way around this problem. Not faster ships, but different kinds of travelers. The first alternative that usually comes up is suspended animation. Put the crew to sleep, slow their metabolism down to almost nothing, and let the decades pass while their bodies barely age. This is a staple of science fiction for a good reason. It would solve the problem elegantly if it worked. The crew boards, falls asleep, and wakes up decades later, still young, still capable, ready to build a new world. The trouble is that human biology doesn't cooperate. We know of animals that can enter states resembling suspended animation. Some frogs freeze solid in winter and thaw out alive in spring. Tardigrades can dry themselves out almost completely and survive in that state for years. Bears enter a form of hibernation that slows their metabolism significantly, though not nearly as much as fiction imagines. But nothing in nature does what science fiction asks suspended animation to do for humans, safely pausing a fully grown human body for decades and reviving it undamaged. The obstacles are severe. Water inside human cells forms ice crystals when frozen, and those crystals tear cell membranes apart from the inside. Cryoprotectant chemicals can reduce this damage, but they introduce their own toxicity at the concentrations required. The brain is especially vulnerable, since the intricate connections between neurons that store memory and personality are extremely sensitive to any disruption. Freeze a person today with current technology, and you don't get a person who wakes up later. You get tissue damage that no known medicine can repair. Some companies do offer cryonic preservation, freezing people shortly after they've passed, in hopes that future technology might one day revive them. But this is a hope, not a demonstrated capability, and no one has ever been successfully revived from it. Building a version of suspended animation reliable enough to keep a crew alive and mentally intact for decades of interstellar travel would require breakthroughs in cellular biology and neuroscience that simply don't exist yet, and there's no guarantee they ever will. Even partial progress, like slowing metabolism moderately through drugs or induced torpor, only buys you a fraction of the time you'd need and introduces serious risks of organ damage and muscle loss over long durations. So suspended animation remains, for now, a beautiful idea sitting just out of reach. The second alternative is even stranger. Skip the body entirely. If the problem is keeping fragile human biology alive for decades or centuries, why not transfer human minds into a form that doesn't age, doesn't need food, and doesn't need to breathe? Digital consciousness, uploaded minds, traveling to the stars as pure information rather than flesh. A ship carrying digital minds could be tiny, compared to one carrying living bodies. No need for farms, no need for air recycling on a massive scale, no need for medical bays or centuries of food production. Just computing hardware, radiation shielding for the electronics, and enough power to keep the systems running. Such a ship could potentially travel much faster, since it wouldn't need to protect a fragile human body from acceleration forces, radiation, or the psychological strain of confinement. It's a genuinely elegant solution, on paper. But it depends entirely on something we have no idea how to do, and no strong evidence we ever will. We don't currently understand consciousness well enough to know if it can be transferred from a biological brain into a computer at all. The human brain contains around 86 billion neurons, connected by an estimated 100 trillion synapses, each one encoding some fragment of memory, personality, or skill through its particular strength and pattern of connection. Mapping that structure with the precision required to preserve a person's identity is a task beyond anything current neuroscience can attempt. Even if we could map it, we don't know whether running that map on a computer would actually produce consciousness, or merely a very detailed simulation that behaves like the person without any inner experience at all. This is one of the deepest unsolved questions in philosophy and neuroscience, sometimes called the hard problem of consciousness. And it hasn't been resolved despite decades of serious attention. There's also the uncomfortable question of what happens to the original. If your brain is scanned and the pattern copied to a computer, does your consciousness transfer to that new substrate, or does a copy of you begin existing while the original you, sitting in the scanning chair, simply continues on as before, unaware that anything happened? Most philosophers who've studied the problem lean toward the unsettling possibility that uploading would create a copy, not a transfer, meaning the original person watching their own upload complete would still be exactly where they started, mortal and unchanged. For interstellar travel, that's a serious problem. You might be sending a copy of a person to the stars while the original stays behind, which raises hard questions about whether you've actually solved anything or just built an elaborate way of creating new people who happen to remember someone else's life. Digital minds remain a fascinating possibility for the distant future, but as a near-term solution to interstellar travel, the technology and the philosophy behind it are both far too unresolved to build a mission around. A third alternative sidesteps the human body altogether, at least at first. Instead of sending grown adults, send frozen embryos. A small robotic ship, far lighter and faster than anything carrying living crew, could carry thousands of human embryos in a dormant state along with the artificial wombs and robotic caretakers needed to grow and raise the first generation once the ship arrives. Since embryos are tiny and require far less life support than living adults during the journey, a ship like this could be dramatically smaller and lighter, allowing it to reach much higher speeds and arrive sooner than a crewed vessel ever could. No one would have to endure the psychological toll of centuries in transit, because no one conscious would be aboard for the crossing at all. The first humans would only exist once the ship reached its destination and began the process of growing and raising them. It's a genuinely clever idea, and some researchers have proposed serious versions of it. But it comes with problems just as severe as the ones it solves. Preserving embryos through decades or centuries of radiation exposure and mechanical stress is itself an unsolved technical challenge, since even small amounts of radiation damage to genetic material could cause serious defects in the resulting children. Raising human infants requires enormous amounts of physical affection, social interaction, and emotional responsiveness that we still don't fully understand, let alone know how to replicate with robotic caretakers. Children raised without adequate human contact in historical cases of extreme neglect have suffered severe and lasting developmental damage. And we have no idea whether even the most sophisticated robotic system could avoid repeating that outcome across an entire founding generation. There's also a profound ethical weight to this scenario that's hard to ignore. The first humans born under this plan would open their eyes in a metal ship or on an alien world with no human parents, no cultural inheritance passed down through lived relationships, and no one to explain what it means to be human beyond what a database can provide. They would be the first entirely orphaned generation in the history of our species, raised by machines, tasked with rebuilding civilization from instructions left by people who had been gone for centuries before they were even born. Whether a healthy, functioning society could emerge from that starting point is genuinely unknown, and the risk of catastrophic failure, of children growing up without the psychological foundations that healthy humans need, is significant enough that most serious researchers treat embryo ships as a fallback idea rather than a primary plan. There's a fourth path worth mentioning, mostly to explain why it doesn't solve the problem at all. Send robots instead of people. Autonomous probes, powered by artificial intelligence, could be launched toward distant stars without any concern for life support, radiation shielding for biological tissue, or the psychological toll of confinement. They could gather data, take images, analyze atmospheres, and beam the results back to Earth across the light years. In fact, we're already doing versions of this, on a small scale, with probes like the ones that have left our solar system and continue transmitting data from the edge of interstellar space. Proposals like Breakthrough Starshot have even suggested sending fleets of tiny, gram-scale probes toward Alpha Centauri using laser-propelled light sails, potentially reaching a meaningful fraction of light speed and arriving within a couple of decades. This is genuinely valuable science, and it will likely happen in some form long before any crewed mission leaves the solar system. But it doesn't answer the question this video is actually about. Robotic exploration tells us about distant worlds. It doesn't put human beings on them. If the goal is understanding, robots are wonderful. If the goal is survival, spreading humanity beyond a single fragile planet as insurance against the risks that could end us here, whether from asteroid impacts, supervolcanoes, engineered pandemics, or the simple, patient fact that every star eventually changes and every planet eventually becomes less hospitable, then robots accomplish nothing. A probe can tell you a planet has breathable air. It cannot breathe that air for you, and it cannot carry forward human culture, language, art, or memory to a new home. For humanity to actually become a multi-planetary and eventually a multi-stellar species, human beings, in some form, have to physically go. And that brings us back to the option we started with. Send whole, living, breathing human societies and let the journey itself be measured not in a single lifetime, but in generations. This is the core idea behind a generation ship. Instead of trying to make the journey short enough for one human lifetime, you accept that the journey will be long, and you design a vessel capable of sustaining a functioning, self-sufficient human civilization for as long as it takes to arrive. The people who board will grow old and be gone before the ship reaches its destination. Their children will grow old and be gone too. And their children's children, born in the vast emptiness between stars, having never seen Earth or felt real wind or looked up at a sky that wasn't a curved metal ceiling, might finally be the ones who step onto new ground. It sounds almost mythic when you describe it that way, and in a sense it is. But underneath the poetry, it's an engineering proposal, one with roots stretching back more than a century to the early 1900s, when the Russian rocket pioneer Konstantin Tsiolkovsky first wrote about self-contained, self-sufficient space habitats capable of supporting humans away from Earth, and later described the need for multiple generations of passengers on a voyage between the stars. The rocket pioneer Robert Goddard explored a similar vision in his own writing around the same era, imagining an interstellar ark carrying its crew across enormous spans of time. The idea was refined over the following decades into more detailed proposals for what became known as world ships, developed by physicists, engineers, and science fiction writers alike ever since. Because unlike faster-than-light travel or digital consciousness, nothing about a generation ship requires new physics. Every individual piece of technology a generation ship needs already exists in some form today. We know how to build closed-loop life support systems, even if not yet at the scale required. We know how to create artificial gravity through rotation. We know how to shield against radiation, grow food in controlled environments, and recycle water and air with remarkable efficiency. What we don't have is the ability to combine all of these systems at the scale of a vessel that has to function perfectly or close to it for centuries, with no possibility of resupply, no rescue mission, and no way to call home for help that could arrive in less than 4 years, even as a radio message. This is why generation ships are often described as being 90% an engineering problem and only 10% a physics problem. And it's also why so many researchers consider them the most realistic path to the stars available to us with anything resembling current or near-future technology. Not because they're easy, because everything else is harder or impossible or built on foundations that don't exist yet. So, what would a generation ship actually look like? Most serious designs share a similar basic shape, dictated less by imagination and more by the harsh requirements of physics and biology. The ship needs to be enormous, likely several miles long, because it has to carry not just people, but entire ecosystems capable of feeding, sheltering, and sustaining them for centuries. Many proposals favor a rotating cylinder or torus shape, spinning slowly around its central axis to create artificial gravity through centrifugal force, pressing inhabitants gently outward against the inner hull in a way that feels, from the inside, remarkably like standing on solid ground. This isn't science fiction speculation. It's basic physics that engineers have studied in detail since at least the 1970s, when NASA funded serious studies into large-scale rotating space habitats capable of housing thousands of people. The rotation rate has to be carefully tuned. Spin too fast, and the difference in centrifugal force between someone's head and their feet becomes noticeable and disorienting, causing nausea and balance problems. Spin too slow, and you don't generate enough force to feel like meaningful gravity at all. For a habitat large enough to feel comfortable, one that doesn't require inhabitants to constantly adjust to strange sensations of tilting or drifting, engineers generally estimate you need a structure at least a mile or more in diameter, rotating gently, once every minute or so. That scale alone tells you something important. This isn't a ship you build the way we build spacecraft today. It's closer to constructing a small, self-contained world, assembled piece by piece, likely in orbit, using materials mined from asteroids or the moon, rather than launched at extraordinary cost from Earth's surface. Some of the more detailed proposals suggest building the ship inside a hollowed-out asteroid, using the rock itself as both structural material and radiation shielding. A strategy that solves two enormous engineering problems at once, by using mass that's already sitting in space, rather than mass that has to be lifted out of Earth's deep gravity well. Other designs favor building from scratch, using metals and composites manufactured in orbit, giving engineers more control over the final shape, but requiring an industrial base in space that doesn't currently exist. Either way, the ship itself would likely take decades to construct, requiring the kind of sustained, multi-generational commitment of resources that no single nation has ever attempted for a single project. And that only becomes plausible if humanity's presence in space grows substantially beyond what it is today. Powering and propelling something this massive is its own enormous challenge. Because a generation ship doesn't need to be fast in the way a probe does, it changes the propulsion calculation considerably. You're not racing against a single human lifetime anymore, so you don't need antimatter or breakthrough physics. You need something reliable, something that can run continuously or intermittently for decades, and something that can be refueled or maintained using resources gathered along the way or carried at launch. Most serious proposals for generation ship propulsion center on nuclear fusion. A fusion drive would work by fusing light elements, typically isotopes of hydrogen, together to release enormous amounts of energy, similar to the process that powers the sun itself, and using that energy to accelerate propellant out the back of the ship for thrust. Fusion offers a combination of high energy density and relatively abundant fuel that chemical rockets simply cannot match. And unlike antimatter, the raw materials for fusion, isotopes like deuterium, exist in reasonable quantities in seawater and in the outer planets of our own solar system. The challenge is that controlled, sustained nuclear fusion for power generation has proven remarkably difficult to achieve, even on Earth, where research reactors have only in the past few years managed to produce brief moments where the reaction released more energy than it consumed. Scaling that up into a reliable propulsion system capable of running for years at a time in the vacuum and cold of deep space, without the benefit of a full industrial supply chain for repairs, is a task that remains firmly in the realm of future engineering rather than current capability. An older and in some ways more immediately achievable idea is nuclear pulse propulsion, sometimes known by the name of an early research effort, Project Orion. The concept, first studied seriously in the late 1950s, involves ejecting small nuclear devices behind the ship and detonating them, with a massive pusher plate absorbing the blast and transferring the resulting momentum forward through a system of enormous shock absorbers. It sounds almost absurd, but the physics checks out. And early studies suggested it could theoretically produce spacecraft capable of reaching a meaningful fraction of the speed of light using technology that, in its basic form, already existed decades ago. The obstacles are less about physics and more about everything else, including the political and environmental complications of launching a ship loaded with thousands of nuclear devices, and the enormous structural engineering challenge of building a pusher plate and shock absorption system capable of surviving thousands of repeated nuclear detonations without breaking apart. A generation ship wouldn't need to accelerate to enormous speeds quickly, either. It could accelerate slowly and steadily over years, using far gentler thrust than a probe racing against a human lifespan would require, easing the strain on both the ship's structure and the people living inside it, most of whom would experience the entire acceleration phase as nothing more than a faint, barely perceptible pull, if they noticed it at all. Whatever propulsion system carries the ship, keeping the people inside it alive is a far more demanding problem than making it move. A generation ship has to be, in the truest sense, a closed loop. Everything the crew breathes, drinks, and eats has to be produced, recycled, and reused almost perfectly, for centuries, without any outside supply arriving to make up the difference. On Earth, this cycle happens naturally, at a planetary scale, plants and oceans and microorganisms constantly cycling carbon dioxide into oxygen, filtering water through soil and rock, breaking down waste into nutrients that feed the next generation of growth. A generation ship has to replicate all of that inside a metal shell, using engineered systems instead of a planet's worth of biosphere. And it has to do it with essentially perfect efficiency, because even a small leak or a slow imbalance, compounded over decades, becomes catastrophic. Consider water. The International Space Station currently recycles roughly 90% of the water used aboard it, filtering everything from sweat and breath condensation to, quite literally, urine back into drinking water. That's an impressive figure for a station that's still regularly resupplied from Earth. A generation ship would need recycling rates far closer to 100%, since even a small percentage of loss every year would add up to a critical shortage over a journey lasting centuries. Air presents a similar challenge. Oxygen has to be continuously regenerated, typically through a combination of algae or plant-based systems and mechanical electrolysis, splitting water molecules into hydrogen and oxygen using electrical power. Carbon dioxide, the natural byproduct of human breathing, has to be scrubbed from the air constantly and either converted back into oxygen through photosynthesis or otherwise processed and stored, because a buildup of carbon dioxide in a sealed environment quickly becomes dangerous, causing headaches, confusion, and eventually loss of consciousness long before oxygen levels alone would become a problem. Food is perhaps the most complex piece of the puzzle, because unlike air and water, it can't simply be filtered and reused. It has to be grown over and over, indefinitely. Most serious proposals imagine vast agricultural sections of the ship, essentially indoor farms using hydroponic or aeroponic systems, growing crops without traditional soil, under carefully controlled artificial lighting, tuned to the specific wavelengths plants need for efficient photosynthesis. Some designs include livestock, smaller animals like chickens or fish that can be raised in enclosed systems and provide protein, dairy, and eggs, while others rely more heavily on plant-based nutrition, algae, and lab-grown proteins. Since raising larger animals requires significantly more space, water, and feed per unit of nutrition produced. Calculating exactly how much farmland a given population would need, accounting for crop failures, pest outbreaks, and the psychological importance of dietary variety over multiple centuries, is one of the most detailed and least glamorous parts of generation ship design. And yet, it may be the single factor that determines whether a mission succeeds or fails. A ship that runs out of food isn't a ship that fails gracefully. It's a ship where every single person aboard eventually starves, with no rescue possible and nowhere else to go. Beyond keeping people fed and breathing, a generation ship has to protect them from an environment that is actively hostile to human biology in ways most people rarely think about. On Earth, we're shielded from the worst of space's radiation by two things: our planet's magnetic field, which deflects charged particles from the sun and beyond, and our thick atmosphere, which absorbs much of what gets through. Outside that protection, in the open environment of interstellar space, a ship and its inhabitants would be constantly bombarded by two main sources of dangerous radiation. The first is solar radiation, streams of charged particles released by stars, including our own sun, sometimes in relatively steady streams and sometimes in violent bursts called solar flares or coronal mass ejections. The second, and in some ways more troubling, source is galactic cosmic radiation, extremely high-energy particles that originate from distant supernovae and other violent events across the galaxy. Particles moving so fast and carrying so much energy that they can pass straight through several inches of aluminum, the kind of material used to shield most current spacecraft. Chronic exposure to this radiation over months is already a serious concern for astronauts on relatively short missions, increasing the risk of cancer, damaging the central nervous system, and potentially impairing cognitive function over time. For a generation ship, where inhabitants would spend their entire lives, and generations of descendants would spend their entire lives inside this environment, radiation isn't a mission risk to be managed for a few months. It's a permanent condition of daily existence that has to be solved, essentially, completely, or the ship's population will suffer rising rates of cancer, genetic damage, and reproductive complications with every passing generation. Shielding against this level of radiation requires mass, and lots of it. Water is one of the most effective and practical shielding materials available, since its hydrogen content is particularly good at absorbing and scattering high-energy particles, which is one reason many designs propose surrounding living quarters with the ship's water supply, using tanks and reservoirs as a dual-purpose barrier that protects the crew while also serving as a resource. Densely packed materials such as polyethylene, a common plastic, performs similarly well for the same reason: its hydrogen content. Some designs that use hollowed-out asteroids for the ship's structure gain a significant advantage here, since many yards of solid rock provide substantial shielding, almost for free, without needing to launch or manufacture the material separately. Even with heavy shielding, though, no design can reduce radiation exposure to zero, and most serious proposals accept that inhabitants of a generation ship would face a somewhat elevated lifetime radiation dose compared to people living on Earth, a trade-off that mission planners would need to weigh carefully against the benefits of reaching a new world, and one that underscores just how much a generation ship asks of everyone who lives and is gone aboard it. Solving the engineering problems of shelter, food, water, air, and radiation only gets you halfway to a viable generation ship. The other half of the equation is people, and specifically, how many of them you need to bring, because this turns out to be one of the most mathematically unforgiving parts of the entire project. A generation ship isn't just a vessel, it's a small, closed human population that has to remain genetically healthy across many generations without any new people ever joining from outside. Population geneticists have studied this problem extensively in the context of endangered species conservation, where small, isolated populations face a well-known danger called inbreeding depression, a gradual accumulation of harmful genetic traits that occurs when a population is too small and too closely related, reducing fertility, weakening immune function, and increasing the rate of genetic disorders with each successive generation. Early estimates for how many people a generation ship would need to avoid this fate were surprisingly small. Some studies from decades ago suggested numbers as low as a few hundred people might be sufficient if genetic diversity were carefully managed. More recent and more rigorous analyses have pushed that number significantly higher. A widely cited study using detailed computer modeling of human genetics concluded that a starting population of around 98 people, if genetics were perfectly managed, through careful selection of who has children with whom across every generation, might be the bare theoretical minimum, but that this number carries essentially no margin for error, accidents, disease outbreaks, or unexpected loss of individuals with rare or valuable genetic traits. Other researchers, taking a more cautious approach and accounting for the reality that you can't perfectly control human reproduction across centuries without creating deeply troubling ethical problems around who is allowed to have children with whom, have suggested that a genuinely safe starting population would need to number in the thousands, somewhere between 4,000 and 10,000 people, in order to maintain healthy genetic diversity without requiring the kind of controlled breeding programs that most people would find morally unacceptable. That's a significant difference, and it matters enormously for the practical design of the ship, since a population of 10,000 requires vastly more space, food production, air and water recycling capacity, and social infrastructure than a population of a few hundred. It also raises a harder question underneath the math, which is how you actually maintain genetic health across centuries without either coercing people's reproductive choices in ways that violate their basic autonomy, or accepting the risk that natural human relationship patterns, who happens to fall in love with whom, will eventually concentrate the population's genetics in ways that increase health risks for future generations. Some proposals suggest storing a supplementary bank of frozen sperm and eggs collected before launch, allowing genetic diversity to be reintroduced through artificial insemination at key points during the journey, without requiring anyone to be told who they can and cannot choose as a partner. This approach threads a difficult needle, preserving both genetic health and personal freedom, but it requires storage technology capable of keeping genetic material viable for centuries, another engineering challenge that hasn't yet been solved at the scale required. Numbers and genetics only describe the biological requirements for a generation ship to survive. They say nothing about whether the people aboard would actually want to keep going, generation after generation, toward a destination none of them chose and none of them will ever see. This is where the project stops being purely an engineering question and becomes something closer to a question about human nature itself. Consider what it would actually mean to be born partway through the journey. You wouldn't be a passenger in any meaningful sense, since you never made the choice to leave Earth, never weighed the risks, never volunteered for anything. You would simply exist, from your very first memory, inside a metal world that curves upward at the edges, breathing air that machines produced, eating food that other people grew under artificial light, knowing that everyone around you and everyone who came before you, back to your great-grandparents, had lived and been gone without ever setting foot on solid, natural ground beneath an open sky. Maintaining a sense of shared purpose across that kind of gap is one of the least understood aspects of the entire generation ship concept, and arguably the hardest one to solve with engineering alone. The founding generation, the people who actually chose to board, would carry a powerful sense of mission. They would remember Earth. They would understand exactly why they made this extraordinary sacrifice, and they would likely be deeply committed to the goal. But that commitment has to somehow transfer intact across generations who never made that choice, who never knew Earth as anything other than a story told by elders and a collection of images stored in the ship's archives. History gives us some perspective here, though the comparisons only stretch so far. Religious communities, isolated settlements, and long-distance seafaring cultures have all managed, with varying degrees of success, to maintain shared purpose, culture, and identity across multiple generations without direct contact with their point of origin. The Pacific Islander societies, who settled remote islands across the vast expanse of the Pacific Ocean over many centuries, developed rich oral traditions, precise navigational knowledge, and strong communal structures that carried their culture forward, even as individual voyages and settlements pushed further from their ancestral homelands. But even the longest and most successful of these journeys lasted years, not centuries, and none of them involved a population permanently sealed inside a single confined structure with no possibility of ever leaving before the final destination was reached. A generation ship would need something more deliberate than the organic cultural transmission that guided historical voyages. It would likely require carefully designed education systems, ceremonies, and cultural institutions specifically built to reinforce the mission's purpose across every single generation, treating the ship's history and destination almost as a foundational story woven into daily life. Similar in function to the origin stories and shared narratives that have anchored human communities and cultures throughout our entire history on Earth. Whether any designed culture, however carefully engineered, could actually sustain that sense of meaning and commitment across 20 or 30 generations. Roughly the number a centuries-long voyage would involve remains genuinely unknown because nothing like it has ever been attempted. Governance presents its own set of difficult, largely unprecedented questions. Who leads a generation ship, and how are they chosen? A single, all-powerful commander sounds appealing for maintaining order and consistent decision-making, but concentrating that much power in one person, generation after generation, creates an obvious risk of the kind of abuse and corruption that has undermined isolated authority structures throughout human history. From ship captains on long ocean voyages to leaders of remote colonial outposts, a more democratic structure, with elected leadership and broad public participation in major decisions, better reflects most modern values around self-governance. But democratic systems can be slow, and a ship facing a sudden crisis, a hull breach, a disease outbreak, a critical system failure, may not have time for lengthy debate and voting procedures before a decision needs to be made and acted upon. Most detailed proposals suggest some kind of hybrid system, a professional, technically trained council responsible for the ship's critical operational systems, life support, propulsion, and structural maintenance, paired with broader democratic institutions responsible for social, cultural, and resource allocation decisions that affect quality of life and shared values. Even this kind of balanced structure faces a harder underlying problem, which is how you prevent political factions, disagreements, and power struggles from threatening the physical safety of a population that has absolutely nowhere to escape to if conflict turns serious. On Earth, when political conflicts become severe, people can sometimes emigrate, form new settlements, or physically separate themselves from a conflict. None of that is possible aboard a sealed vessel traveling through interstellar space. Every disagreement, every grudge, every ideological split has to be resolved within the same enclosed population, using the same limited resources for as long as the journey lasts, which for many proposed missions could easily span 300 years or more, roughly 10 to 12 human generations, depending on average lifespan and the age at which people typically have children. Some researchers have suggested that generation ships would need something like a formal constitution, a foundational set of rules and values established before launch, deliberately designed to be difficult to change, in order to protect basic rights and prevent any single generation from making decisions that permanently and irreversibly harm future generations who have no voice in decisions being made in their name. Today, designing a governance system robust enough to function well for centuries, flexible enough to adapt to circumstances the original founders couldn't possibly have anticipated, and fair enough to maintain the trust and cooperation of a population that includes people from many different backgrounds, values, and life experiences, may honestly be a harder problem than any of the purely technical engineering challenges the ship also has to solve. Education becomes just as critical as governance, because a generation ship can never afford to lose specialized knowledge. Every system aboard the ship, from the fusion reactor to the water recycling plants to the agricultural bays, requires skilled people who understand not just how to operate it, but how to repair it, maintain it, and eventually replace worn-out components using whatever manufacturing capability the ship carries. On Earth, if a particular skill becomes rare, society can usually compensate. Training new specialists takes years, but the broader population and economy absorb that gap without catastrophic consequences. On a generation ship, if the last person who deeply understands a critical life support subsystem is gone before they've fully trained a successor, that knowledge might be permanently lost. And a ship that loses too much of this kind of specialized expertise over time faces a slow, compounding decline that could ultimately threaten everyone aboard. This means education aboard a generation ship can't function the way it does on Earth, as a relatively loose system where people can pursue whatever careers interest them, and society simply adapts to whatever mix of skills the population happens to produce. It likely needs to function more like a carefully managed pipeline, ensuring that critical skills, engineering, medicine, agriculture, and systems maintenance are always being taught to enough people, with built-in redundancy, so that the accidental loss of a few specialists doesn't create a crisis. At the same time, an education system that felt purely utilitarian, training people only for functional roles the ship needs, would likely fail to sustain a genuinely healthy, meaningful human society, one that also needs art, philosophy, history, and simple curiosity in order to keep people psychologically and culturally whole across the long, enclosed decades of the journey. Balancing these two needs, practical necessity and human flourishing, is another design challenge with no perfect historical precedent to draw from. Healthcare presents equally difficult questions across a multi-century timescale. A generation ship would need doctors and medical facilities capable of handling everything from routine illness to complex surgery, childbirth, and the particular health challenges created by long-term exposure to elevated radiation and a partially artificial environment. Unlike Earth, there's no possibility of specialists flying in for a rare case. No possibility of importing a new medication that hasn't yet been synthesized aboard the ship. No possibility of sending a critically ill patient somewhere better equipped to help them. Every medical capability the ship might ever need has to either be present at launch or be something the ship's population can develop and manufacture on its own, which means carrying not just medical supplies, but the underlying scientific and industrial capacity, chemistry labs, manufacturing equipment, and trained researchers to continue advancing medical knowledge and treatment throughout the journey, rather than simply relying on what was known and available back on Earth at the moment of departure. There's also a quieter, more personal challenge that doesn't show up in engineering diagrams or population models, and that's simply what it feels like, psychologically, to live an entire human life inside a sealed vessel with no possibility of leaving. Researchers who study isolated and confined environments, including Antarctic research stations, submarine crews, and astronauts on long-duration space missions, have identified a range of psychological effects that tend to emerge over extended periods in enclosed, unchanging environments. A sense of monotony can set in, since the same walls, the same corridors, the same artificial lighting, and the same limited group of people day after day, year after year, can wear on the human mind in ways that aren't always obvious until they've already taken hold. Interpersonal tensions tend to intensify in small, closed groups. Since there's no possibility of putting distance between people who are struggling to get along, no new social circles to seek out, no possibility of simply moving away from a difficult relationship or a lingering conflict. Some researchers have described a phenomenon, sometimes called third quarter syndrome, where morale and psychological well-being tend to dip noticeably once a mission passes its halfway point. As the initial excitement of departure fades and the eventual relief of arrival still feels impossibly distant. For a mission that lasts a single Antarctic winter or a single long spaceflight, these effects, while serious, are temporary and end when the mission concludes. For a generation ship, there is no ending within any single person's lifetime, no relief of a return trip, and no fresh start waiting at a specific, foreseeable point in one person's future. Every single person born aboard the ship, apart from the very last generation lucky enough to actually witness the arrival, will live their entire life inside an environment that never fundamentally changes, without ever standing under an open sky or breathing air that wasn't produced by a machine. And the psychological weight of that reality is arguably the least studied and least understood variable in the entire concept of generation ships. Some proposals attempt to address this through careful ship design, incorporating varied environments within the vessel, different types of spaces, gardens, open communal areas with long sightlines that reduce the feeling of confinement, simulated changes in lighting that mimic day and night cycles, seasons, and even simulated weather, in an effort to give inhabitants some of the sensory variety and environmental richness that a human mind evolved over hundreds of thousands of years on an open planet to expect and need. Whether that's enough to sustain genuine long-term psychological well-being across generations who have never known anything else, and therefore have no real basis for comparison, is a question no one can currently answer with confidence, because it has simply never been tested at this scale, or for anything close to this duration. Assuming all of these challenges can be solved structurally, biologically, socially, and psychologically, the next question is simply, where would a generation ship actually go? Not every star makes sense as a destination, and choosing one involves weighing distance against the likelihood of finding something worth centuries of sacrifice at the other end. Alpha Centauri, the closest star system to our own, is the obvious first candidate, sitting about 4 light-years away, made up of 3 stars, Alpha Centauri A, Alpha Centauri B, and the smaller, dimmer Proxima Centauri, which orbits the other 2 at a considerable distance. Proxima Centauri has drawn particular scientific interest because it hosts at least one known planet, Proxima Centauri b, orbiting within what astronomers call the habitable zone, the range of distance from a star where temperatures could theoretically allow liquid water to exist on a planet's surface. But Proxima Centauri is a red dwarf star, smaller, cooler, and far more prone to violent flares than our Sun. And a planet orbiting close enough to sit in its habitable zone would likely be bombarded by intense radiation and stellar activity that could strip away its atmosphere entirely, making it a far less hospitable destination than its habitable zone status might initially suggest. Alpha Centauri A and B, the 2 largest stars in the system, are more similar to our own Sun, and any planets found orbiting them at the right distance could potentially be more Earth-like in terms of stellar environment, though as of now, no confirmed planets have been detected around either star, leaving this possibility genuinely open but scientifically unconfirmed. Slightly further out, the TRAPPIST, one system has captured enormous public attention since its planets were discovered, since it hosts 7 roughly Earth-sized worlds, several of which sit within the star's habitable zone. TRAPPIST, one sits around 40 light-years from Earth, considerably further than Alpha Centauri, but the sheer number of potentially habitable worlds in one place makes it an intriguing target, even though, like Proxima Centauri, it's a small, cool red dwarf star with its own concerns about flare activity and atmospheric stability for closely orbiting planets. Tau Ceti, a Sun-like star about 12 light-years away, is another frequently discussed candidate, offering a more familiar stellar environment than the red dwarf systems, along with evidence of multiple planets, though questions remain about whether any of them sit at a genuinely habitable distance. The honest truth is that as of today, we haven't confirmed a single planet beyond our solar system that we know, with real confidence, could support human life without extensive modification. Every candidate carries significant uncertainty, and choosing a destination for a mission that can't be redirected once it's truly underway means accepting a level of risk that would make even the most confident scientists uneasy. Launching toward a world we've only ever observed as a tiny dip in a star's light, or a handful of pixels through the most powerful telescopes we've ever built, hoping that centuries later, our understanding proves correct. This uncertainty points toward one of the more likely real-world versions of a generation ship, at least in its earliest stages, which is a mission that doesn't commit to a single, specific destination at the moment of launch. Instead, the ship might depart with a general direction and a handful of candidate systems, while continuing to gather astronomical data throughout the early decades of its journey, refining its understanding of which target actually offers the best chance of success, and adjusting course while adjustments are still physically possible, long before the ship reaches the point where changing direction would cost more energy and time than the mission could afford. This approach would require a ship's population to include not just engineers and farmers and doctors, but working astronomers, constantly observing, calculating, and refining the mission's understanding of its own destination throughout the journey, effectively continuing humanity's search for a new home even after departure, rather than treating that search as something that ended the moment the ship left Earth's solar system. Once a destination is finally locked in and the ship begins its approach, decades before actual arrival, an entirely new phase of extreme risk begins: deceleration. A ship that has spent a century or more slowly accelerating to a meaningful fraction of light speed carries an enormous amount of kinetic energy, and slowing back down requires essentially the same amount of effort and fuel that was needed to speed up in the first place. Careful, sustained thrust in the opposite direction, beginning years or even decades before the ship reaches its target system. This deceleration phase places enormous stress on a ship's structure and systems that by this point have already been operating continuously for centuries, subject to the slow accumulation of wear, fatigue, and unexpected failures that come with any machine, however well maintained. Operating far beyond any timescale similar machines have ever been tested against. If a critical propulsion or structural system fails during this final, most demanding phase of the journey, after centuries of travel and the lives of 10 or more generations invested in reaching this point, the mission could still fail catastrophically, either overshooting the destination entirely with no ability to correct course, or arriving too fast to safely enter orbit, turning the final chapter of an extraordinary multi-century journey into its most dangerous moment. This is part of why some researchers argue that the deceleration and arrival phase deserves just as much engineering attention and redundancy as the initial launch itself. Since a mission that succeeds for 300 years only to fail in its final decade represents perhaps the cruelest possible outcome for the many generations who lived and were gone along the way, each of them contributing to a goal they trusted the ship and the generations before them to eventually achieve. Even if the ship survives its long crossing and successfully decelerates into its target system, arrival isn't a finish line so much as the beginning of an entirely new and equally dangerous phase. Whatever data the ship gathered from Earth, and whatever it refined during its own centuries-long observation of the target system, still has to be confirmed up close. Because subtle details, invisible from light years away, the exact composition of an atmosphere, the presence of harmful microorganisms, unexpected weather patterns, or geological instability, can only be fully understood once the ship is actually in orbit, deploying probes and eventually landers to gather direct, close-range data. If the target planet turns out to be genuinely habitable, matching or exceeding what the ship's population expected, the process of actually settling it would still unfold cautiously, likely beginning with small groups of trained specialists descending to establish initial habitats, test the local environment directly, and confirm that human biology can actually cope with a new world's specific gravity, atmospheric pressure, radiation levels, and any unfamiliar biological or chemical hazards the planet might present. Only gradually, as confidence grows, would larger portions of the ship's population begin to transition down to the surface, likely over a period of years rather than all at once. maintaining the ship itself as a fallback shelter and resource base until the new settlement can truly stand on its own. If, on the other hand, the target world turns out to be uninhabitable, whether due to inaccurate earlier data, unexpected environmental changes over the centuries since the ship departed, or simply an atmosphere or surface too hostile for practical settlement, the ship's population would face an extraordinarily difficult choice, with no good options. Some proposals suggest that a well-designed generation ship should carry enough remaining resources and propulsion capability to continue on to a secondary candidate system if the primary destination fails. Though this would mean asking a population that has already endured centuries of confinement to commit to potentially decades or centuries more, extending a journey that everyone aboard had been told their entire lives was nearing its end. Other proposals suggest establishing at least a temporary presence, even on a marginally habitable world, using advanced life support and terraforming technology to slowly modify the environment over further generations, effectively continuing the mission's spirit of patient, multi-generational sacrifice even after physical arrival, transforming the challenge from crossing interstellar space into the perhaps equally difficult challenge of transforming an entire planet into something humans can eventually inhabit without artificial assistance. There's no way to know, with any real confidence, which of these outcomes a real mission would actually face, because it depends entirely on details about specific worlds that we currently cannot observe with enough precision from Earth. And it's part of what makes committing an entire population's future to a single interstellar journey such an extraordinarily high-stakes gamble. One where success isn't guaranteed, even after centuries of travel and flawless engineering. Given everything we've covered so far, the sheer scale of engineering required, the unresolved questions around genetics, governance, education, psychology, and destination, it's worth stepping back and asking a more fundamental question, one that has nothing to do with whether we could build a generation ship and everything to do with whether we should. This is where the conversation moves, from engineering into ethics, and it's a genuinely difficult territory because it involves weighing competing values that don't reduce neatly into a single right answer. On one side of this argument sit those who believe that ensuring humanity's long-term survival justifies extraordinary sacrifice. Even sacrifice imposed on people who never had any say in the matter. Earth, however stable it feels day to day, is not permanently safe. Asteroid impacts have reshaped the history of life on this planet before, and while we now have some capability to detect and potentially deflect large incoming objects, smaller, still devastating, impacts remain difficult to predict with much warning. Supervolcanic eruptions, the kind that have occurred periodically throughout Earth's geological history, could trigger years of global cooling and agricultural collapse severe enough to threaten modern civilization. Beyond natural threats, humanity has also created new risks entirely of its own making, from the possibility of global nuclear conflict to engineered pandemics to the long-term uncertainties around advanced artificial intelligence, risks that didn't exist a century ago and that we still don't fully understand how to manage. From this perspective, a generation ship, however imperfect and however much it asks of the people who live and are gone aboard it, represents a form of insurance for the species as a whole, ensuring that even in the event of a catastrophe severe enough to end civilization or human life entirely on Earth, some portion of humanity, its knowledge, its culture, its capacity to build and create and continue, survives somewhere else, carrying forward everything that makes us who we are. On the other side of this argument sit those who point out, quite reasonably, that the people born aboard a generation ship after its initial launch never consented to any of this. They didn't choose confinement. They didn't choose a life without ever seeing an open sky. They didn't choose to be born into a mission that demands their entire existence be organized around a goal they'll likely never personally witness being achieved. Every generation after the first is, in a very real sense, conscripted into a project through the simple, unavoidable fact of being born aboard the ship, with no meaningful alternative available to them. Is it ethical to create an entire multi-generational lineage of people specifically to serve as the crew and cargo of an extraordinarily long, difficult, and genuinely dangerous voyage, particularly when there's no certainty the mission will even succeed in the end? Reasonable people land in very different places on this question, and it's worth sitting with the discomfort of that disagreement rather than rushing past it, because it reflects something true about the trade-offs involved in almost any large, multi-generational human project. From building cathedrals that took centuries to complete, to establishing colonies whose founders never intended their descendants to have any real choice in continuing that legacy. Some thinkers have proposed ways to soften this ethical tension, even if they can't fully resolve it. One idea suggests that every generation aboard the ship should retain a genuine, structurally protected right to alter or even abandon the mission, meaning that if a majority of the population at any point decided the voyage should end, whether by turning back, by settling somewhere less ideal but reachable sooner, or by some other collective choice, that decision would be honored, rather than overridden by the wishes of a founding generation who are long gone and can no longer weigh in. This would mean building flexibility and genuine self-determination into the ship's governance from the very beginning, rather than treating the original mission plan as a fixed, unquestionable commandment passed down unchanged across centuries. Critics of this approach point out a practical problem, since a ship's fuel, trajectory, and life support systems are all calculated based on very specific assumptions about the mission's duration and destination, and a population that decided partway through to abandon the original plan might find that the ship's remaining resources don't actually support many meaningfully different alternatives. In practice, once a generation ship is far enough into its journey, the options available to any given generation may be more limited than the ideal of full self-determination would suggest, simply because of the hard physical constraints of fuel, life support capacity, and structural design. Another proposed approach focuses less on structural flexibility and more on transparency and honest cultural framing from the very start, ensuring that every generation aboard genuinely understands, without illusion or forced positivity, exactly what kind of life they were born into and why, treating the mission's purpose as something to be openly discussed, questioned, and even challenged rather than something enforced through unquestioned tradition or authority. Proponents argue that even if people born aboard the ship never had the option to choose otherwise, at minimum, they deserve full honesty about their circumstances and a genuine, ongoing voice in decisions that affect their lives and the lives of their own children, rather than being treated merely as a means to an end determined centuries earlier by people they never met. None of these approaches make the underlying ethical tension disappear entirely. They simply represent different ways of trying to treat that tension with the seriousness it deserves, rather than pretending it doesn't exist, or rushing past it in the excitement of imagining humanity's expansion to the stars. It's worth pausing here to imagine, concretely, what the different chapters of a generation ship's journey might actually feel like for the people living through them. Because the abstract engineering and ethical questions we've covered so far only tell part of the story. Picture the founding generation first, the people who actually choose to board. They would likely be selected through an extraordinarily rigorous process, chosen not just for technical skill in engineering, medicine, agriculture, and science, but for psychological resilience, cooperative temperament, and a genuine, deeply examined commitment to a mission they understand they will never see completed. Their departure from Earth would be, in every meaningful sense, permanent and final. Communication with anyone left behind would still technically be possible in the earliest years. Radio messages sent and received across the growing distance. But even in the first decade of travel, those messages would already be taking months, then years, to arrive, turning what began as conversation into something closer to a slow, one-directional exchange of letters into an increasingly distant past, since a return message might take just as long to arrive as the ship itself had already traveled since asking the question. Within a generation or two, communication with Earth would likely become largely symbolic, an occasional transmission acknowledged decades later, more a ritual reminder of where the journey began than a genuine ongoing relationship with the world humanity left behind. Now, picture a middle generation, born perhaps a century or more into the journey. People who have never seen Earth, who know it only through stored images, recordings, and the accumulated cultural memory the ship has deliberately worked to preserve. For them, the ship isn't a vessel on a mission, it's simply home, the only home they've ever known, with its own internal geography, its own local history, its own traditions and inside jokes and disputes between neighboring sections that likely feel every bit as real and consequential to them as any conflict between nations ever felt to people on Earth. They would grow up, fall in love, raise children, build careers, maintaining the ship's systems or growing its food or teaching its next generation, and eventually grow old and be gone, having spent their entire lives contributing to a goal that remains, for them, permanently in the future. Something their own great-grandchildren might see, if all continues to go well. There's something almost unbearably poignant about that reality when you actually sit with it, an entire human life, full of the same joys and struggles and small daily meanings that fill any life, spent entirely in service of an arrival its owner will never personally witness. And finally, picture the last generation, the ones lucky, or perhaps simply fortunate in the timing of their birth, to actually be alive when the ship finally reaches its destination. For them, the abstract mission that shaped every generation before them suddenly becomes real, tangible, immediate. The culmination of a promise made by people who have been gone for centuries, finally coming due, carried forward faithfully across dozens of generations who each did their part, maintained the systems, raised the children, taught the lessons, and kept the ship and the mission alive. Given everything involved, the engineering, the genetics, the governance, the psychology, the ethics, it's fair to ask whether humanity is anywhere close to actually attempting something like this, or whether it remains purely theoretical. An interesting thought experiment with no real path toward implementation. The honest answer is that we're genuinely far from ready, but perhaps not as far as the sheer scale of the challenge might initially suggest. Serious organizations have already begun studying pieces of this puzzle in detail. Icarus Interstellar, a non-profit research organization founded by scientists and engineers, has spent years developing detailed technical studies for interstellar propulsion concepts, including refined versions of fusion-based drive systems. The 100-Year Starship Project, an initiative that received early funding through DARPA, brought together researchers from multiple disciplines specifically to study the long-term, multi-generational challenges involved in eventually sending humans beyond our solar system, treating the problem not as a single engineering project, but as a genuinely interdisciplinary challenge spanning biology, sociology, ethics, and physics, alongside traditional aerospace engineering. University research groups have run detailed computer simulations modeling everything from the minimum viable population needed for genetic health to the social dynamics of small, isolated communities to the practical agricultural yields required to sustain a population over centuries inside an enclosed habitat. None of this research has produced anything close to a finished mission plan, and it's important to be honest about that. But it represents genuine, serious scientific engagement with the problem, treating generation ships not as pure science fiction, but as a legitimate, if extraordinarily distant, engineering goal. Realistically, most researchers who study this area suggest that a genuine generation ship mission, if humanity ever attempts one, is likely centuries away from actually launching. Not because the core physics is impossible, but because so many supporting technologies and capabilities need to mature first. We would likely need a substantially more developed presence in space, generally, permanent settlements on the Moon or Mars, industrial capability to mine and process materials directly in space, rather than launching everything from Earth's surface, and much more advanced, thoroughly tested closed-loop life support systems, probably first proven at smaller scales in space stations and off-world colonies, before anyone would responsibly commit thousands of lives to a multi-century voyage with no possibility of rescue. In that sense, a generation ship isn't really a project humanity would build directly, so much as it's a natural, eventual extension of a much longer process of humanity gradually becoming a spacefaring civilization, learning to live sustainably off Earth in ever more ambitious and self-sufficient ways, until eventually the technology, the population, and the accumulated experience exist to make a truly independent, self-contained interstellar voyage plausible rather than reckless. It's also worth returning, one more time, to why so many researchers keep circling back to generation ships specifically, rather than continuing to hold out hope for one of the faster, more dramatic alternatives. It isn't because generation ships are the most exciting option, or the most elegant, or the one that feels most like the futuristic visions many of us grew up imagining. It's because, when you actually lay every serious proposal side by side and weigh them honestly against both the laws of physics and the current trajectory of human technology, generation ships are the only approach that doesn't require betting humanity's future on a breakthrough we have no current path toward achieving. Faster than light travel, wormholes, and warp drives all require physics that, as far as our best current understanding goes, may not simply be undiscovered, but may actually be fundamentally impossible, since they would require forms of matter and energy with properties nothing we've ever observed in the universe actually possesses. Suspended animation requires solving cellular and neurological preservation challenges that remain almost entirely unsolved, despite genuine scientific interest and effort. Digital consciousness requires not just extraordinary technology, but resolving open philosophical questions about the nature of identity and experience that thoughtful people have debated for generations, without reaching consensus. Embryo ships require raising entire founding populations of children with no direct human caregivers, a scenario with deeply troubling psychological and ethical implications that most researchers are reluctant to treat as a primary plan. Generation ships, by contrast, require no new physics, no unsolved neuroscience, no resolved philosophy of mind. They require scaling up and integrating technologies we already understand, in principle, closed-loop life support, artificial gravity through rotation, radiation shielding, sustainable agriculture, and reliable, long-duration propulsion into a single, enormously ambitious, enormously difficult, but fundamentally achievable engineering project. That doesn't make generation ships easy, and it doesn't resolve any of the genuinely difficult ethical questions about consent and sacrifice that we've spent considerable time exploring tonight. But it does explain why, decade after decade, as other more exotic proposals rise in popular imagination and then quietly fail to produce workable engineering paths forward, generation ships keep returning to serious scientific conversation as the most credible, most grounded answer to a question humanity may eventually have no choice but to answer for real. There's a strange kind of symmetry worth noticing here, one that connects this entire concept back to something deep in our own history as a species. Long before anyone imagined ships crossing the emptiness between stars, small groups of early humans were already doing something not entirely unlike this, on a much smaller, but still remarkable, scale. Tens of thousands of years ago, groups of our ancestors left the region where our species first evolved and began spreading outward across unfamiliar land, coastlines, and eventually oceans, into environments no human had ever encountered before, carrying with them no certainty of what they would find, no ability to return easily if conditions proved harsh, and often no realistic expectation that the people making that journey would personally benefit from wherever it eventually led. Entire communities settled unfamiliar coastlines, developed the tools and knowledge needed to survive in radically different climates, and passed that hard-won understanding down to children and grandchildren, who would, in turn, continue pushing further, generation after generation, into landscapes their own ancestors could never have imagined. We are, all of us alive today, descended from people who made choices very much like the ones a founding generation of a starship crew would face, choosing uncertainty over the comfort and familiarity of what they already knew, trusting that whatever came next was worth the risk, not necessarily for themselves, but for whoever came after them. In that light, a generation ship isn't really a departure from human nature, so much as it's an extension of a pattern that has defined our species since long before recorded history began, this restless, sometimes reckless, often extraordinary willingness to commit ourselves, and the futures of people we will never meet, to journeys whose full outcome we cannot possibly know in advance. The difference this time is scale, and the difference is honesty. Our ancestors who crossed unfamiliar oceans or unfamiliar continents often had little real understanding of what awaited them, and made those journeys with whatever partial knowledge and instinct they had available. A generation ship, by contrast, would launch with centuries of accumulated scientific understanding behind it, with detailed calculations, careful genetic planning, deliberately designed governance, and open-eyed acknowledgement of exactly what the people aboard and their descendants would be asked to endure. That level of foresight doesn't make the sacrifice smaller, and it doesn't resolve the ethical weight of asking generations yet unborn to carry forward a mission they never chose. But it does mean that if humanity ever does build a ship like this and sends it out into the dark towards some distant point of light we've spent centuries studying and hoping about, it would be doing so with its eyes fully open, understanding precisely what it was asking and choosing, deliberately and with full knowledge of the cost, to ask it anyway. One question tends to come up whenever this topic is discussed seriously, and it deserves honest attention rather than a quick dismissal. Why not simply wait? If suspended animation or digital consciousness or genuinely faster propulsion might eventually become possible through future scientific breakthroughs, wouldn't it make more sense to delay any generation ship mission, potentially by centuries, until those better options are actually available, rather than committing thousands of lives to the much harder, much longer path we've spent this entire video exploring? It's a reasonable instinct, and many serious researchers do, in fact, argue for exactly this kind of patience, suggesting that humanity should continue developing its presence within the solar system, continue researching more advanced propulsion and life extension technologies, and hold off on any irreversible, centuries-long commitment until better options are genuinely on the table. But there's a counter-argument worth taking just as seriously, one that centers on risk rather than optimism. Every year, humanity remains confined entirely to a single planet is another year where a single, sufficiently severe event, whether natural or human-made, could end our species entirely, with no backup, no continuation, nothing left of everything we've built and become across our entire history. Waiting for better technology assumes that better technology is actually coming, and coming within a time frame that matters, an assumption that, however reasonable it might feel, isn't actually guaranteed by anything we currently know. Some risks humanity faces don't wait politely for us to finish researching better solutions before they arrive. From this perspective, a generation ship, however imperfect, however much it asks of the people who build and crew it, represents something valuable, specifically because it doesn't depend on any breakthrough that hasn't happened yet. It can, in principle, to be attempted with technology. Humanity is already capable of developing, given enough time, resources, and collective will. Rather than technology, we can only hope future generations of scientists might someday discover. There's also a version of this argument that doesn't require choosing definitively between waiting and acting. Many researchers who study interstellar travel suggest that humanity's realistic path forward likely involves pursuing multiple approaches simultaneously, rather than committing exclusively to any single strategy. Continuing to develop faster propulsion research and life extension science in parallel with the slower, more grounded work of eventually preparing for a generation ship, so that whichever approach matures first or proves most viable, given whatever we learn along the way, humanity isn't left without options simply because it bet everything on a single technological path that failed to materialize in time. There's another practical consideration that rarely gets discussed outside of specialist circles, but matters enormously to how a real generation ship mission might eventually be planned, and that's redundancy. A single ship, however carefully engineered, represents a single point of failure for an entire mission, an entire population, and in some framings, a meaningful fraction of humanity's hope for survival beyond Earth. If that one ship suffers a catastrophic, unrecoverable failure, whether from a structural flaw, a systemic biological crisis, or simply an accumulation of small problems that compound over centuries into something unsurvivable. The entire effort, along with everyone who ever lived and was gone aboard it, would be lost, along with every resource and every year of preparation invested in making the mission possible in the first place. Because of this, many serious proposals argue that a genuinely responsible interstellar migration effort wouldn't send a single-generation ship at all, but rather a small fleet, multiple independent vessels, launched together or in relatively close succession, each carrying its own separate population, its own separate life support systems, and, ideally, its own separate destination, or at least enough independence that a failure aboard one ship wouldn't doom the others. This approach mirrors a principle already well understood in engineering and risk management more broadly, that redundancy protects against single points of failure, and that distributing risk across multiple independent systems dramatically increases the odds that at least one succeeds, even if others encounter problems along the way. A fleet approach would multiply the resources and coordination required enormously, essentially demanding that humanity build and launch several complete generation ships rather than just one, which pushes the timeline for actually achieving something like this even further into the future than a single ship mission already requires. But it also reflects a more honest reckoning with just how much uncertainty surrounds every part of this endeavor, acknowledging that even the most careful engineering and planning cannot guarantee success across a mission spanning centuries, and that if humanity is serious about using generation ships as genuine insurance against existential risk, that insurance policy is considerably stronger with several independent attempts than with all of our hope resting on a single vessel and a single population, however well prepared they might be at the moment of departure. Step back far enough from all of this, past the engineering diagrams, the population models, the governance debates, and the ethical disagreements, and a generation ship starts to look like something more than just a mission. It becomes a message, sent forward, not across distance alone, but across time, carrying everything a civilization has learned, valued, and built, into a future none of its original architects will ever personally witness. Every system aboard such a ship, every carefully preserved seed bank, every stored recording of music and language and history, every lesson passed from one generation of crew to the next about how to keep the water clean and the air breathable and the reactor stable represents a kind of inheritance, deliberately, painstakingly carried forward by people who understood they were building something for others, not for themselves. That's not an entirely unfamiliar idea, even here on Earth. Every parent who plants a tree they'll never sit in the shade of, every scientist who spends a career on research whose full benefits won't be realized for decades, every builder of a cathedral, a library, or an institution meant to outlast its founders by centuries, is participating in some smaller version of the same basic impulse, a willingness to invest effort and care into something whose true value will only be realized by people the builder will never meet. A generation ship simply takes that same impulse and stretches it to its absolute limit, asking not just one act of forward-looking care, but an entire civilization's worth of sustained, uninterrupted commitment held steady across dozens of generations toward a goal that remains, for almost everyone involved, permanently just out of reach. Whether humanity ever actually builds one is, honestly, still an open question, dependent on choices, priorities, and technological developments that haven't happened yet, and might unfold very differently than anything we've discussed tonight. But the fact that serious scientists, engineers, and philosophers have spent decades thinking carefully through every layer of this problem, from the genetics of small populations to the psychology of enclosed environments to the ethics of unconsented sacrifice, suggests that this isn't simply an idle fantasy borrowed from science fiction. It's a genuine reflection of something humanity keeps returning to, again and again, across our entire history. The conviction that reaching beyond what's immediately possible, even at extraordinary cost, even without any guarantee of success, is somehow worth attempting. Not despite the difficulty, but because of it. It's also worth imagining, briefly, what the alternative future looks like, the one where humanity simply never attempts anything like this at all. In that future, human civilization remains permanently confined to a single planet, orbiting a single, ordinary star, for as long as that arrangement continues to work. For a very long time, that might be perfectly fine. Earth has supported human life for hundreds of thousands of years, and there's no specific reason to expect it will suddenly stop doing so tomorrow, or next year, or even within most of our own lifetimes. But permanence isn't something any planet can promise indefinitely. Our own sun, currently in a stable phase of its life that has lasted billions of years and will likely continue for billions more, will eventually change, growing brighter and hotter as it ages, gradually making Earth less habitable long before it ever becomes the kind of dramatic, swollen red giant sometimes depicted in illustrations of a star's distant future. That process is almost incomprehensibly far off, more distant in time than human civilization has existed by an enormous margin, and it's not the kind of risk that should drive urgent decision-making today. But it does illustrate a basic truth that no planet, including our own, offers truly permanent shelter, and that a species which never develops the capability to exist anywhere else remains, indefinitely, entirely dependent on the continued cooperation of a single world, a single star, and an unbroken chain of fortunate circumstances stretching indefinitely into the future. A species confined to one planet is also, in a more immediate sense, more fragile than one that isn't, since any single catastrophic event, however unlikely in any given year, carries the full weight of ending everything, with no backup anywhere else to continue what was lost. Generation ships represent one possible answer to that fragility, an attempt, however difficult and however far from certain, to give humanity a genuine foothold beyond the reach of any single planetary catastrophe. They're not the only conceivable answer, and they're certainly not guaranteed to succeed even if humanity does eventually attempt one. But among the realistic options available to a civilization still bound by the physics we currently understand, they may be the only answer that doesn't require waiting indefinitely for a breakthrough that might never come. And that alone is a significant reason. So many people who study this question seriously keep returning to it, decade after decade, as something worth continuing to refine, study, and prepare for, even knowing that the actual mission, if it ever launches at all, likely remains many generations away from us right now. None of this happens in a single leap, either. If humanity does eventually build something like a generation ship, it almost certainly won't be the first major step we take beyond Earth, but closer to one of the last, in a long sequence of smaller, more achievable milestones, stretching across generations before the ship itself ever leaves. Long before anyone seriously attempts a centuries-long voyage to another star system, humanity would likely need to establish permanent, genuinely self-sufficient settlements much closer to home, on the Moon, on Mars, and potentially among the asteroids scattered throughout our own solar system, each one serving as a real-world proving ground for exactly the kinds of systems a generation ship would eventually depend on. A lunar settlement, for instance, would force engineers to solve many of the same closed-loop life support challenges a starship requires. Recycling air and water with extremely high efficiency, growing food in fully artificial, enclosed environments, and managing radiation exposure without the protection of a thick planetary atmosphere, all while remaining close enough to Earth that mistakes, at least in the early years, don't carry the same absolute, irreversible finality they would for a ship already committed to an interstellar crossing. A Mars settlement would push those same systems further, testing them across a genuinely multi-year supply gap, since, even with Mars relatively close by cosmic standards, resupply missions from Earth still take months to arrive, forcing any Martian colony to develop real independence rather than simply relying on a steady stream of support from home. Settlements built within the asteroid belt, harvesting metals, water, and other raw materials directly from small bodies scattered throughout the solar system, would begin to demonstrate the kind of space-based industrial capability that would eventually be needed to construct something as enormous as a generation ship, without having to launch every single component out of Earth's deep gravity, well at extraordinary cost. Each of these steps, individually, is already a genuinely difficult, multi-decade undertaking in its own right. And humanity has really only just begun the earliest stages of attempting any of them. But taken together, they represent a realistic, if slow, pathway, one where each new settlement, each new technological milestone, each hard-won lesson about keeping people alive and thriving in an artificial environment gradually builds toward a level of capability where a mission as ambitious as a true generation ship stops being a purely theoretical exercise and starts becoming something humanity could genuinely, responsibly attempt. We are, right now, standing at the very beginning of that long sequence, closer to its first tentative steps than to anything resembling its conclusion, which is precisely why a mission that might not launch for another century or more is still worth thinking about carefully today, since the foundational choices and the foundational values we build into humanity's earliest steps off this planet will likely shape what any eventual generation ship looks like, and what kind of civilization it ultimately carries toward the stars. So, where does all of this actually leave us? Generation ships are not science fiction in the sense of being pure fantasy, disconnected from real physics and real engineering. Every individual system they would require, closed-loop life support, artificial gravity through rotation, fusion or nuclear pulse propulsion, radiation shielding, sustainable agriculture already exists today in some working form, even if none of it has ever been combined and scaled to the level a real mission would demand. They are also not an easy, guaranteed path to the stars. Every layer of the challenge, from population genetics to governance, to the sheer psychological weight of an entire life spent inside a sealed, unchanging environment, remains only partially understood, and some of it may simply never be fully solvable in a way that removes all risk and all ethical discomfort. And yet, when every other proposed alternative is weighed honestly against what we currently know about physics, biology, and technology, generation ships remain the only approach that doesn't require humanity to simply wait, hoping for a breakthrough that may never arrive. In fields like faster-than-light propulsion, cellular preservation, or the nature of consciousness itself, breakthroughs that decades of dedicated research haven't yet produced, and cannot promise to deliver on any particular timeline. That's not a comfortable conclusion. It doesn't offer the clean, exciting vision of humanity effortlessly zipping between stars that science fiction has trained so many of us to expect. Instead, it offers something slower, heavier, and in many ways, more honest. A vision of interstellar travel achieved not through a single dramatic breakthrough, but through patient, multi-generational commitment, sustained by ordinary people living ordinary lives, raising children, maintaining systems, teaching lessons, generation after generation, each one trusting the ones who came before them, and each one, in turn, trusted by the ones still to come. Would you board a ship like that, knowing you would grow old and be gone long before it ever reached its destination? Would you choose to have children aboard, knowing they would inherit a mission they never agreed to, a metal sky they never chose to live beneath? Would you trust that the people generations after you, people who will never know your name or remember your face, would honor the sacrifice you made on their behalf, the same way you would be asked to honor the sacrifice of the generation who boarded before you were even born? These aren't questions with easy or comfortable answers, and they may not need to be answered by anyone alive today. But if humanity ever truly commits to becoming a species that exists beyond a single planet, beyond a single star, these are the questions that commitment will eventually demand we answer. Honestly, and without illusion, because the ship, if it ever launches, will carry not just people and provisions across the dark between the stars, but every value, every compromise, and every hard choice that went into deciding it was worth attempting at all. There's one more way to think about all of this, one that doesn't require resolving any of the difficult ethical questions we've spent this video sitting with, but that might help explain why the idea continues to hold such a powerful grip on scientists, engineers, and dreamers alike. Decade after decade, despite every obstacle standing in its way. For nearly 4 billion years, life on this planet has followed a consistent pattern, spreading into every available niche, every survivable environment. No matter how difficult or seemingly inhospitable, from the deepest ocean trenches under crushing pressure and total darkness, to boiling volcanic vents, to the driest deserts, to the frozen poles. Wherever there has been even the faintest possibility of survival, life has found a way to reach it, adapt to it, and eventually thrive within it. Not through any single dramatic leap, but through countless small generations, each one slightly better adapted than the last, patiently extending life's reach a little further than it had gone before. Humanity, in a very real sense, represents the latest and most capable expression of that same ancient pattern. A species that didn't just adapt to its environment the way earlier life forms did, but learned to actively reshape environments, build tools, and eventually construct entirely artificial spaces, from heated homes in freezing climates to pressurized stations beneath the ocean, extending our own reach into places our bodies alone were never suited to survive. A generation ship, viewed through that lens, isn't really something separate from the rest of life's long history on Earth, so much as it's the next expression of the exact same underlying pattern. Life patiently, persistently, extending its reach into an environment that seems, at first glance, completely hostile to it, using whatever tools and adaptations happen to be available at the time, and trusting that patience, incremental progress, and generations of accumulated effort can eventually accomplish what no single dramatic attempt ever could. Whether humanity ultimately succeeds in building and launching a ship like this, whether it arrives centuries or 1,000 years from now, or whether the whole idea eventually gives way to some entirely different approach that hasn't been discovered yet. The underlying impulse, driving all of it, this deep, patient willingness to reach beyond the world we were born into and to trust the effort forward to people we will never meet, may be one of the truest expressions of what it means to be part of life's very long, very persistent story on this planet, and perhaps, eventually, beyond it. It helps, too, to remember just how young humanity's presence in space actually is. The first human being only reached orbit in 1961. The first footsteps on another world came just 8 years after that. In the span of a single long human lifetime, we've gone from having no capability to leave our own atmosphere at all, to routinely operating a continuously crewed station in orbit, landing rovers on Mars, and sending probes past every major planet in our solar system and beyond its outer edge entirely. Measured against that pace of change, the idea of eventually building something as ambitious as a generation ship stops looking quite so impossibly distant, even if it remains, honestly, many generations away from becoming a real, funded mission, rather than a subject for careful study and speculation. Every closed-loop life support system tested aboard a space station today, every lesson learned from months-long isolation studies, every incremental improvement in growing food off-world or shielding astronauts from radiation is, in its own small way, a single brick laid toward a foundation that a future generation, one we can't yet picture clearly, might eventually build upon. So the next time you look up at the night sky and pick out a single point of light, remember that reaching it, really reaching it, with human beings still alive and breathing and building at the other end, likely won't come down to some sudden flash of genius, some elegant equation that finally cracks faster than light travel wide open. It will more likely come down to something far less glamorous and far more human, thousands of ordinary people choosing, generation after generation, to keep the water clean, the air breathable, the crops growing, and the mission alive, passing that responsibility carefully from hand to hand across centuries, trusting each other across a gap of time none of them will ever personally bridge. That's the terrifying part, and it's also, in its own quiet way, the beautiful part. Generation ships ask everything of the people who build and crew them, and offer, in return, no guarantee, no certainty, only the possibility that somewhere far ahead, generations after everyone currently living has long since been gone, a group of descendants who never knew Earth firsthand might finally step outside, breathe air that wasn't manufactured by machines, and look up at a sky that isn't curved metal, but something real, something new, something their ancestors spent centuries reaching toward without ever seeing it themselves. Whether humanity ever actually takes that leap remains, for now, an open question, one that will likely be answered by people not yet born, using technology not yet built, facing choices we can only begin to imagine from where we stand today. But the fact that we're already asking the question, already working through the engineering, the ethics, and the sheer human weight of what a journey like that would actually require, suggests that some part of us has already decided the answer is worth pursuing, no matter how long it takes or how many generations it demands along the way. Thank you for spending this time with me tonight, thinking through one of the strangest, most demanding, and most quietly hopeful ideas humanity has ever seriously considered. If this exploration of generation ships gave you something to think about, consider sharing it with someone who loves these questions as much as you do. And I'll see you next time, as we keep looking up and keep wondering what's out there, waiting for us to finally arrive. Good night.